What's happening? Uh-huh.
On Friday or Saturday, I'll be in an area and I'm not sure it's sufficient yet physically.
You'll be in the felt.
Yes.
Alright. We'll see how it goes. Just keep me posted. We'll see how it goes. Just keep me posted. Yeah. So the summary is surprisingly short, by the way. But yeah, in grades 10 and 11, the lessons for one movement in one dimension, right, are for rectilinear motion. So in other words, movement that goes either left to right or back and forth, depending on how you look at it. Bless you. Right? So rectilinear motion is this, right? Rectilinear motion. So it's when you have an object and it's moving either in that direction or in that direction, right? Back and forth or front to back. Now, just a little bit about one dimension. I'm sure you've heard in woke conversations, yeah, this 3D material existence, etc. Have you heard anything like that? Yeah. Okay, that's cool if you didn't hear it from woke, because the natural scientific concept applies in pretty much all the conversations you can imagine. But what I wanted to do is, if you have a dot on the surface, right, or a line, right, let's say you have just a dot. Let's start with just the dot. And between you and I, one of us is so small that we can fit in and on the dot. Right? In and on the dot. So that means our interaction with the world does not exceed the boundaries or the confines of this dot. Right? Obviously, if now we're being practical, there might be something that's larger than whomever's occupying that dot, and that's something or someone that's larger, let's say it creates an opportunity for the person or object or thing that can move and interact with the world to move from where the dot is to the end of this line there. Right? Now, this movement will be possible, and whomever can move from this point to that point and then stop, but they can also move from the same point back to where they started and then stop. But their motion will continue on and on and on and on in that direction. We call this 1D. Right? Now, once we introduce, and in math you can sort of think about this as like the number line or the x-axis, right? If you want to think about it mathematically. X-axis or number line. Now, let's say whoever created this plane of existence, this dimension of existence for the person that is small enough to fit in and on that dot, and they introduce another axis. So now they introduce another dimension of motion. And now our little fella can move in that direction, then stop there, then travel in that direction, then stop there, then go there and stop there. And they're free to roam, but let's say we set up a rectangle and they can't go outside of that rectangle. But it doesn't matter. Any motion that they take, be it it's directly from this bottom all the way up, or from this end all the way to that other end, right? They the person moving in this block, whenever they move, their motion has got an X direction and a Y direction. So if they're gonna move from, let me make a different color just to illustrate the example. I wanna make that same illustration but with a different color. So let's say they're moving in this red direction, like so, right? They're moving in that red direction, like so. So they're starting there and they're moving all the way to that point and they're gonna stop there. Now that motion, if this is the X direction and that's the Y direction, the second dimension, they will move first in the X direction that way, and then they will move second in the Y direction in that way. So ultimately they will have gone from where they start, which is at this corner here, and then change direction and go up there until they end up there. So they moved in that direction, the X direction, and in the Y direction, and their resultant is way over there, right? Now we call this two dimensions because they have one axis, which is the X that they can operate and navigate in, and another direction, which is Y, which they can operate and then move in. Now I just want to finish off with this talk of dimensions and introduce a third dimension, and this is something we got introduced to in first year science and I guess maths for engineering, right? So let's say that's our x-axis again and that's our y-axis again. So okay, sorry. Right. So remember this axis, x and y, in the previous page. Remember the previous page, we have x and y. This one here. That one I just circled. You see that? Yeah. So we're gonna take that same axis and then just twist it around a bit. So it went from being x, y, and now there's imagine at the point 0, 0, where x and y cross, there's a line sticking out vertically, right? That line sticking out vertically, we'll call it the x-axis. That introduces a third dimension into our scenario. So the first dimension was rectilinear motion, which was pretty much motion in the x direction, just going back and forth, right? That was the first dimension. Then the second dimension becomes the y-axis, and the last dimension becomes the z-axis, which is height. So that would be, if you want to think about a box sitting on the floor or even the corner of your wall, any wall where two walls intersect, right? This would be the one wall, this would be the other wall, and this would be the corner inside the wall. The yellow line would be the corner inside the wall. You see that? Such that if you were to put a box it would be sitting like this somehow, right? Our box would look something like that. That one. Now that's where the idea of 3 dimensions comes into place, right? And that's the nature of the world that we live in, the physical dimension of existence that we live in, right? So I just wanted to clarify that, so that when we talk about one-dimensional projectile motion, we understand that we're only going to focus on one dimension. Now in grade 10 and 11, I suppose, the motion was often limited to back and forth, left and right. So that was in the x direction, right? Now in grade 12, we're going to revisit the same concepts, but this time we're going to look at objects that are moving from the ground all the way up. Oh yeah. So next we're going to look at objects that move all the way up and down vertically. And examples of this include scenarios where people are throwing up balls or objects, or dropping objects from a certain height, right? And we're gonna analyze these projectiles, and these are called projectiles. Projectile, right? So projectiles, okay, let me make next slide. So projectiles these are objects that move through the air, right? You ever seen in those war movies they always talk about projectiles referring to missiles? Yeah, so we're gonna do the basic calculations that start off that conversation. So we're gonna look at objects that move through the air, that's projectiles, and we deal with objects that are affected, or subjected rather, that are under the influence or subjected to gravity. And they move only vertically. Only vertically is important. Vertically. Alright. Now the second important thing is that these objects, they are on Earth, because that's pretty much our frame of reference, and they accelerate at a constant rate. That rate is called g, acceleration due to gravity. And we're going to write that g, because it's a vector, with a little bar or arrow on top of its head. And this g has a magnitude of 9.8 meters per second. Now, depending on how you're approaching the problem to solve it, you can either choose upwards as positive, but that would mean the acceleration due to gravity in your calculation will be a negative value, so it would be negative 9.8. So if you choose the upward moving direction as positive, then because the acceleration due to gravity, which pulls objects towards the center of the earth, meaning relative to something that's in the air, that acceleration acts downwards, which is towards the center of the earth. That acceleration is directed towards the center of the earth, So if your convention in any calculation is up is positive, then that g is negative. So direction of g is toward center of Earth. Third, the time it takes to rise to a maximum height. Now this is something you must know before we get in. When an object travels up, before it travels down, it takes a certain amount of time and then it reaches its maximum height. So ball gets thrown up, then it reaches a maximum height. On the way back down, it will reach the same height it was at, let's say at x, where we first noticed its motion. It will reach this height. It will reach this height at more or less the same time it took to go up. So in other words, the time to travel up is the same amount of time to travel down for the object. And we can simply say that time for object to travel up equals time to travel down, right? But this depends. So if an object is thrown from height x, it takes a certain amount of time to go up. Then to come back down will take the same amount of time to come back to height x. But if it goes beyond to maybe height, let's call that height y1. Let's say it travels to height y2, then the time is not equal. So I just wanted to make that clear, right? The magnitude of the velocity will also be the same, but the direction will be the reversed. So velocity to travel up equals velocity to travel down. All right. This is known as time symmetry, and it is a consequence of uniform gravitational acceleration. So we'll call this time symmetry. You know what symmetry means? What does it mean?
The same people.
On either side, right? Also, if you think about a butterfly, its axis of symmetry is right in the middle of its body, such that the one wing on the left mirrors exactly the one wing on the right. So that line in the middle is axis of symmetry. And it's nice that we're doing this now, because in functions, we're going to deal with a lot of symmetry concepts in math. But yeah, you'll see how these two are working in tandem. All right. So this time symmetry is a consequence of acceleration due to gravity, which is constant, which is rather uniform. So uniform means it's the same throughout. Just like uniform when kids are in school and they dress the same, just to make them look the same. Right? So number 4, there are 4 equations of motion that can be used to solve vertical projectile problems. So 4 equations. So instead of x, I'm going to use y to indicate that we're not moving in the x direction, which is back and forth, left and right, but I'll use y to indicate that we're moving up and down. Right? So we can say the final velocity vector equals initial velocity vector plus acceleration due to gravity times time. That's equation 1. Equation 2 is change in displacement equals initial velocity plus final velocity, all of this over 2 times the time. Equation number 3 is another one here, change in displacement, which equals velocity times the time plus a half acceleration due to gravity times the time squared. And the last equation is v squared v final squared equals v initial squared plus 2 times acceleration due to gravity times change in displacement. So these formulae, just take note of them. They're gonna appear a lot in our program for this chapter. They're gonna appear in almost every problem, right? And lastly, the graphs for vertical projectile motion are similar to graphs for motion at constant acceleration. So let me just make a note of that. Right, so lastly, graphs for vertical projectile motion are similar to graphs for motion at constant acceleration. So when we get to do graphs in the chapter, you'll understand what that implies. And yeah, right, so that table there at the bottom just gives you an indication of the units that we use, as well as what is a vector and which one is not. Right, so just to go back to the start, yeah, so okay, before we go there, so the notes that the learning guides that I gave out make reference to grade 10 units and unit conversions. So just make a note of those books there, those learning guides there, because I did submit in the classroom the different texts that are linked there. So go through them and find the linked concepts. It's these ones here, these 4 here. Route 1. When you peel. Okay, just make a note in your handwritten notes that on page 72, those are the concepts you have to be familiar with to understand this. Yeah. So all of that in the chapter summary starts here, right? I want us to go through the first problem. Yeah. I didn't give you access.
Yes, but I've been asking, maybe it's just been missing because that's why I'm
Ish. Okay. You know what? I always make the mistake already. When I've opened it here in the call, then you've got it. So let me see. Okay, it should be up now. Should be up now. should remember to do this. Hey, tomorrow I must change. Musa's no longer gonna join us, ne? So I will. Right. Yeah. So now I'm back here. I am back. All right. Cool. Okay. So let's do this worked example quick. Let's go as far as we can with it. At least it's worked out, but at least it should be enough to help us with the concept. So on page 77, we have worked example number 1. And we're shown that there's a person who's throwing a ball up. Let me do this. Draw a little bit to the bottom. So she's there, this person throwing a ball up. Right, so the ball is thrown up, and now the image shows us. You're laughing at my sketch? No, because I want to make a better one, so I'll just draw a girl. Ish. I was hoping this would look like someone who's throwing a ball. Yeah. Okay, maybe let me not try to be too.
No, but that's perfect. You've been doing the same one the whole time.
Yeah. Okay, he looks like he's throwing a ball. So yeah, they've thrown a ball up in the air. Boop. You see it now. There's our guy. They've thrown a ball up in the air, our person, right? This ball has moved up. And when it left the hands, its initial velocity was 10 meters per second. And this distance here we're given as 1.5 meters, right? So when the picture was taken, the ball was at a 1.5 meter height above the point of release. And at the point of release, the velocity is 10 meters per second, right? Which is here. So we're required to determine the maximum height that the ball reaches. So in other words, the ball is going to go up and then travel to its maximum height, where it will no longer travel up and then start changing direction until it goes back to the floor or to back where it came from, which was in the thrower's hands. All right. Sharp. So we're given the initial velocity 10 meters per second, and it's going upwards, and the acceleration due to gravity, we know that is 9.8 meters per second. We discussed that in the chapter overview. The acceleration due to gravity is 9 meters per second downwards. So at this point we haven't chosen a convention, but should we choose a convention and upwards is negative, then this will be positive, and should we choose upwards as positive, then that would be negative. So let's just choose upwards as positive, so that you can see how even though we might follow the same calculation, we'll get different signs, but our convention will tell us why we have a certain answer in a certain way. We also need to determine when the ball will be at the position in the photograph. So when we are asked about when, we usually have to find the time, right? So after how long is the ball in that position? All right, and then the ball is thrown straight up and will reach a maximum height, at which point its velocity will be 0. So up here the velocity is 0. That's the point where the ball stops traveling upward and starts changing direction to travel downwards. Is that clear? All right. The height of the ball is 1.5 meters above the initial point, which is what was shown in the picture. So obviously the ball is going to travel much higher than 1.5 meters. So we need to calculate how much high does this ball go. So we've chosen upwards as positive, and now we're going to start solving the problem. So we need to determine how to approach the problem. So even though there are a number of questions to answer, the best approach is to work through one at a time. First, we keep the sign convention. We've got 3 quantities. The first velocity, VI. I guess for the upward motion, this will be final velocity. And we've also got the acceleration due to gravity. So we at least got those 3. Now we can go back to these 4 formulae. 1, 2, 3, 4.
Yeah.
Right? And it looks like it might be worth our while to work with equation 4. So equation 4 is this one here at the bottom.
Yeah.
You see it?
Yes.
Alright, cool.
Final velocity is equal to initial velocity plus gravity times change.
Yeah, in displacement. Right, just a word of caution. It's velocity final squared, right? So the final velocity squared. So velocity final squared equals velocity initial squared plus twice the acceleration due to gravity multiplied by the change in displacement. All right. Now, we know that at this point, the velocity is 0. So our V final is 0. Our initial velocity is 1.5. No, not 1.5. 10 meters per second. So we've chosen positive as upwards. So it will be just positive 10 plus 2 A. Did you just 2 times negative 9.8
Oh yes.
times delta y? We don't know how much high the ball is gonna go from here. So that's what we are going to. So just looking at this part here, this part of the motion here. So we don't know how much this height is going to be. So that's what we're calculating. And that's what we're going to get with delta y. Right? So we're gonna get 0 equals 100 minus 19.6 delta y, negative 100 equals 100 minus 100 minus 19.6 delta y. Do you want to tell me why I put in the negative 100 on the left hand side of the equal sign? Okay, it's just the simple math, additive inverses. Remember, we're making y the subject of the formula. We're solving for y. So we need to manipulate our equation so that we get to the answer. Right? So in solving for y, after adding additive inverses, then we do a similar approach with multiplicative inverses. And we're gonna do that by dividing, so it's minus 100 on both sides, and divide by negative 19.6 on both sides. And this gives us 1, divide by 1, and this should give us, the negative signs divide each other into becoming positive. Therefore, delta y is, when you take 100, negative 100, and you divide it by negative 19.6, what's the answer on your calculator? We're taking negative 100, divide by negative 19.6. Yes, that's what I meant to say. 5.10. Right. Great. So we got that, and that is the correct answer. Now we need to identify the appropriate equation to determine how long. That's the second question, right?
So obviously we don't leave this here. Is there no explanation?
Like explanation for the 5.102.
Like a wording to say, therefore.
Okay, good question. Good, very good question. So now, what we can conclude here, our conclusion, because that's what you're asking, right? Our conclusion here is that, for number 1, is that the ball reaches 5.102 meters above point of release. Because that's what we asked, right? Above point of release before falling back down. That's what we can conclude. The ball reaches 5.102 meters above point of release before falling back down. Now in the second part, we must work out how long it takes for the ball to reach that maximum height. So in other words, we want to calculate if we had a stopwatch in our hands and we started timing when the ball was released, right up to when it stopped going up in mid-air and started coming back down. Right up between, yeah?
How long it takes from point of release to 5 to 10 meters?
Yes. So how long from point of release to maximum height? That's what we're going to calculate next. And we're going to use again another equation of motion. This time it's velocity final equals velocity initial. 15 minutes to go, né? Physics is nice, eh? Physics is nice. Anyway, plus acceleration due to gravity times time. Right. So that's on this page. So we're gonna use this equation. Our final velocity still 0. Our initial velocity is 10. Remember, our convention is upwards is positive, and acceleration due to gravity is therefore negative. And then we multiply by the time, and then we're gonna have negative 10, or rather minus 10 on both sides, so that negative 10 plus 0 equals 10 minus 10 minus 9.8 times t. Can you see what I did there? What did we do? Additive inverses, correct. So negative 10 equals negative 9.8 times t. Then we're gonna divide by negative 9.8 on both sides, so that negative 10 divided by negative 9.8 will equal negative 9.8 t divided by negative 9.8. This gives us 1. And what did we do there? Correct. Multiplicative inverses. Right. And this gives us, how much time is that? When you divide 10 by 9.8? When will
1.02.
1.02. So our conclusion, therefore, it takes 1.02 seconds for the ball to reach I mean eh? I mean the ball could be very light.
5 meters.
I mean, we'd have to run an experiment to see if we can get that height or similar or close enough. Right, so now the third part was for us to determine the time or times when the ball will be at the position shown in the photograph. Now this part is especially needs a special amount of care, and here's why. Let me just get my water bottle. Right, so immediately when the ball leaves the hands, the timer starts, right? Now after maybe a fraction of a second, which I suspect it is a fraction of a second, the ball is at 1.5 meters, which is where the picture shows that its position relative to the thrower, right? Now remember, there's time symmetry. So from the point of release to 1.5 meters above is a certain amount of milliseconds, and then the ball passes that 1.5 meter point, and it reaches this point here at top, right? So from here to here is a couple of microseconds. So at the 1.5 meter distance, it's a couple of microseconds, and then it's 1.02 seconds from point of release all the way to the maximum height. That's 1.02 seconds, the time of travel. Now, we're not only going to find the time it takes to move from point of release to 1.5 meters above, we also have to find the total time around the trip. So in other words, the time it takes to travel from there to there is 1.02 seconds, but we must also find the time it takes to travel there, as well as how long it will take to go up and then come back down to here. So there's another amount of time that we don't know that it will take to reach again that 1.5 meter above the point of release height. Okay, so we're gonna calculate that. Now to calculate that, we're gonna use our equation. So how long to 1.5 meters above release point? That's what we must work out. So we're gonna borrow this equation. Change in displacement equals initial velocity times the time plus a half times acceleration due to gravity times the time squared, right? We do know that the displacement, we do have a value for the displacement, which is 1.5 meters. We have the initial velocity, which is 10 meters per second, and we have the acceleration of the ball. So we've got VI, which is 10 meters per second. We've got G, which is negative 9.8 meters per second squared. And we've got a change in displacement, which is 1.5 meters, right? Now we're going to substitute all of this into the equation up there, so that
Final time of 1.2 seconds.
sorry,
It's irrelevant.
that time is just how long it takes to reach maximum height from point of release. So a fraction of that time is the time it, yes. So we're gonna work out that time component. Yeah, so we have our 1.5 meters, because upwards is positive. That equals 10 times the time plus a half into negative 9.8 times t squared. So the delta y is positive because it's above, it's above the point of release, so that's in the upward direction. So that's why it's positive. All right.
So if we get cut in 2 minutes, when must I join?
Let's end this one
Okay.
and then join on the one on the calendar invite.
You sending another one?
No, just open the calendar schedule on Google and then join on that one. Okay, so far you follow the substitution.
Yes.
Yeah. Then we're gonna do additive inverses. So minus 1.5 on both sides, so that 0 is negative 4.9 t squared plus 10t.
When I try 4.9, you minus the 4.9.
What happens if you multiply 9.8 by half? You get it? The G, the one 9.8
Yes.
has a coefficient of a half. Do you see that? Yes, that's where the 4.9 comes from. You get it?
Opposites.
Alright, so now something looks like it's from math. Can you see what it is? Right, so we have negative 4.9 t squared plus 10t minus 1.5 equals 0. What does that look like? Eh?
What is it supposed to look like? Don't say additive inverse.
No, definitely not additive inverse. Do you see what I've... Okay. Are you still on Jamboard?
Yeah, page 8.
Page 8, okay. It's refreshing. It's taking a bit of time. I don't know why.
Oh, jeez.
And then it all comes at one time.
Yeah.
Alright, cool. So what does this remind you of? Ax squared plus bx plus c. A. What does that remind you of?
Yep, I'm on the question.
It's a quadratic expression.
Yes.
It's a quadratic expression. So we're going to take that quadratic expression and then we're going to solve it using the quadratic formula. Quadratic formula is x minus b plus or minus square root of b squared minus 4ac, all this over 2a. And ours is negative 4.9 t squared plus 10 t minus 1.5 equals 0. Alright? And a is negative 4.9, b is positive 10, and c is negative 1.5. Do you see that? And we're solving this quadratic expression not for x but for t. So on the one part, for the one possible answer, we'll have t is negative b plus square root of b squared minus 4ac over 2a, and the other possible answer is minus b minus b squared minus 4ac, all this is over 2a. Right? You still remember how to use the calculator for this? Right, so we're gonna go with c is negative 1.5, so you go negative 1.5 multiplied by, or let me rather substitute first, so negative into plus 10 plus square root of b is 10 squared, 4 into negative 4.9 negative 1.5 over 2 times negative 4.9, that is negative into 10 minus 10 squared minus 4 into negative 4.9 negative 1.5, all this is over 2 into negative 4.9. Alright, so you start with the negative 1.5 multiplied by negative 4.9 multiplied by negative 4. Let me open my calculator as well. So I go 1.5 negative times 4.9 negative equals, and then I multiply that by 4 negative equals, and then I add that to 10 squared, which is 100 equals, and then I where's square root? I square root the answer, and then I add it to 10 minus equals, then I divide it by 9.8 negative, and that gives us 0.16 seconds. That's the first possible answer. Then I go to the other possible answer, so it's 1.5 negative times 4.9 negative times 4 negative equals plus 100 equals square root of answer, negative that answer, minus 10 equals, and then divide by 9.8 negative, and the answer is 1.878 seconds. So those are the possible answers for the time it takes to get to a height of 1.5 meters above the point of release.
Great.
So on the way up, it takes 0.16 seconds to reach 1.5 meters, and on the way down, that entire travel time from traveling up to changing direction, coming back all the way down, that entire time, and on the way back, and on rather the round trip back to, so it takes 1.878 seconds to travel from point of release let me do this. I made a duplicate, and this is not Word, so I won't get red zigzag lines. From point of release to 1.5 meters on the, or rather above point of release on the way back. Right, and you can just look down there on page 79 how they put it, and you'll sort of formulate your way of responding to these types of questions. But for now we can just end here, and then so tomorrow we're not linking up, ne? But I guess I'll see you Thursday.